This video demonstrates how to model and program embedded multi-core microcontroller boards using CASP. For this demonstration we use some of the popular multi-core microcontroller boards such as ESP32s, Raspberry Pi Pico, Arduino RP2040 Connect, STM32 H745 Nucleo board, and Texas Instruments Launch XL F28379D. Before creating models on any of these boards, ensure that respective board drivers, CASP board support package and other dependencies are properly installed. These details are further elaborated in CASP board support package documentation of respective boards. We start with ESP32s Target. Before creating the model, select the target and set the programmer port to which it is connected, and set appropriate simulation parameters. We create a very basic model with onboard LED blink logic using a pulse generator. We also create a serial port block that connects to host PC. The data output from the serial block is ORed with the pulse generator output and fed to a digital output block mapped to the onboard LED. We connect the serial block in loopback mode and set the send and receive data sizes to 32 bytes. Build the model and program the board. By default the model uses single core out of the available 2 cores. Take a note of the rate at which the LED is blinking. We establish communication with the board from the host PC through the programmer serial port. After the communication has started, you may observe that the LED is blinking at reduced rate compared to earlier. This is because the same core has to run the code of LED blink logic and serial communication. You can also observe that the LED is controlled from the host PC. We now shift some of the blocks to run on the second core. For this we need to first set, limit model compute threads to 2. And shift all blocks to core 0 except serial block which is set to run on core 1. Reprogram the board with the updated model. You may observe that the onboard LED is blinking at much faster rate compared to earlier when single core is used for the entire model. We establish communication with the board from the host PC. After the communication has started, you may observe that the LED is blinking at same rate as earlier. This is because the LED blink and serial communication logic are running on different cores. We now demonstrate how to program Raspberry Pi Pico board using same model and following similar steps. Initially we run the complete model on single core. Take a note of the rate at which the LED is blinking with and without serial communication. As expected, the LED blink rate reduces when serial communication is on, compared to when it is off. Now, we will rerun the model in dual core mode by shifting some of the blocks to the second core. You may notice that, in dual core mode, the serial communication has little effect on the LED blink rate as they are now running on different cores. We now demonstrate how to program STM32 H745 dual-core Nucleo board using similar model and following similar steps. Since this board is pretty fast compared to earlier boards, reduce the simulation time step to 10 microseconds. Because of its heterogeneous architecture, we require a hardware semaphore-based share memory block to share data between the two cores. We use two such blocks, one for read and other for write with matching section index. Memory size and other parameters are chosen to share 4 bytes or 1, 32-bit integer value. Initially we run all the blocks on the first core. Disable the cache on the first core so that the effect of serial port on LED blink rate is more pronounced. Program both the cores one after the other. Take a note on LED blink rate. We will compare this again when using second core. Now shift the serial port block group to the second core. And program both cores again. Now, you can observe that the LED blink rate is much faster than compared to single core mode. LED is controllable from the host PC, indicates that data is being transferred from core 1 to core 0 through shared memory. We now demonstrate how to program Texas Instruments Launch XL F28379D using the same model and following similar steps. Ensure that the Code Composer Studio is installed and the paths are properly configured in CASP as shown in the video. First, configure for single core mode. Set the program to be kept in flash instead of RAM. Ensure all blocks are assigned to core 0. Disable shared memory in single core mode and directly connect the output of tap-out block to input of the OR gate. Take a note of the LED blink rate when serial communication is on and off. Now, enable the shared memory blocks and reprogram the two cores in dual core mode. Set serial port block group to run on core 1 and blink logic on core 0. Since serial port is running on the second core, you may have to enable SCIA manually. First program the second core and then program the first core. Observe that the LED blink rate is not affected by the serial communication. LED is controllable from the host PC, indicates that data is being transferred between the two cores through shared memory. Thank you for watching this video.